Good afternoon, everyone. My name is Donglin Yang. Today, I will give an overview of mathematical optimization, focusing on the basic concepts of convex optimization. Because the time is limited, so I will not cover the technical detail. Here comes the first question. What is optimization? Optimization is the mathematical discipline which is concerned with finding the maximum or minimum of the function, may be subject to many constraints. Basically, the classes of optimization problems are characterized by particular forms of the objective and constraint functions. It includes nonlinear optimization, convex optimization, least squares, and linear programs. If the objective function and constraint function are linear, we call it a linear program. While the optimization problem is not linear, it is called a nonlinear program. But today I just focus on a class of optimization problems called convex optimization, whose objective and constraint functions are all convex. For the convex optimization, there are two widely known and used special subclasses: least squares and linear programs. So, before we go to the detail section, we want to know where could we use the optimization. Actually, optimization is used for problems arising in architecture, nutrition, electrical circuits, in economics, transportation, etc. For most of these applications, optimization is used as of aim to a human decision maker, system designer, or system operator. Realize the application of optimization. Here we come to how to recognize optimization problems. Basically, mathematical optimization problems has the general form just like this, which composes of objectives and constraint functions. Here, the vector x is the optimization variable of the problems, and the function f0 on the real n vector into the real number is the objective function. The function fi on the real n vector into real number are the constraint functions, where I is from n to m, and the constant from b1 to bm are the limits or bounds for the constraints. A vector x bar is called optimal or a solution of the problem if it has the smallest objective value among all vectors that satisfy the constraints. Among the mathematical optimization, there is a special class. We call it convex optimization. It is the problem whose objective and constraint functions are all convex. They must satisfy the inequalities. For all x and y's are in real n vector, and alpha beta are in real numbers, with alpha plus beta equal to 1. Because any linear program is a convex optimization problem, we can consider convex optimization to be a generalization of linear programs. In this section, I will describe one of the very widely used and known special subclass of convex optimization. We call it least squares. The objective function of least squares is a sum of squares terms of form ai transpose multiplied by x minus bi. Here, A matrix is the k by 1 real number matrix, and ai transpose are the row of A matrix. The real n vector X is the optimization variables. Recognizing an optimization problem as a least square problem is straightforward. For example, uh, look at this function. We only need to verify that the objective is a projective function, and then test whether the associated projective forms is positive semi-defined. It's very important symbols. And the least squares problems is the basics for regression analysis, optimal controls, and many parameter estimation and data fitting methods. So it is a very efficient tools to help me to solve some problems. Another important class of optimization problems is linear programs. We notice that the difference between linear and least squares is that the objectives and all constraints of functions are linear. Here, you can see that the vector c and a1 to am are real n vector, and the scalar b1 to bm are in real numbers are problem parameter. Some applications lead directly to linear programs in such forms. In many other cases, the original optimization problem does not have the standard linear programs forms, but we can transform it into an equivalent linear program and use the associated uh, techniques to solve it. After recognizing the convex optimization problems, here comes to another question: how to solve the problems? Actually, the solution of a least square problems can be reduced to solving a set of linear equations. Take this objective function as example. There is an analytical solution. For least square problems, the textbook by Stephen Boyd provides good algorithms for solving the problems to high accuracy and with high reliabilities. The least square problems can be solved in a terms approximately proportions to the square of n multiplied by k with a no constant. A current desktop computer can solve a least square problems with hundreds of variables and thousands of terms in a few seconds. An algorithm and software for solving these scale problems are reliable enough for embedded optimization. And actually, this library are open source in the online. You can text it if you are interested. And indeed, we can say that solving these square problems is a mutual technologies. It can be reliable use by many people who for those who don't even know the detail. However, for the linear programs, there is no analytical formula for the solutions. But there are a variety of many effective methods for solving them, including the interior points method. The term complexity of interior points method is order square of n multiplied by m. The algorithm is quite reliable, though possibly not quite reliable as methods for least square problems. We can also say that it's a multiple technologies to solve the linear programs problems. For the convex optimization, there is in general no analytical formula for the solutions, but there are very effective methods for solving them. For example, the interior points methods works very well in practice, but in some cases, It can be pushed to solve the problems to a specific accuracy with a number of operations. Take this problem as example. It can be solved in a number of steps or iterations that is almost just range between tens and 100 steps. However, solving general convex optimization problems is not yet a mature technology. Research on interior points methods for general nonlinear convex optimization is still a very active research area. For the nonlinear optimizations, it is the term used to describe an optimization problems when the objectives or constraint functions are not linear, but not know how to be convex. Uh, However, there are no effective methods for solving the general nonlinear programming problems. Even some simple looking problems with as few as 10 variables can be extremely challenging, while the problems with a few hundreds of variables can be intractable. Methods for the general nonlinear programming problems, or therefore it will take several different approaches, uh, each of which involves some compromise. Uh, for, for example, in local optimization, the compromise is to give up seeking the optical x, which minimizes the objective over all feasible points. Instead, in local optimization, we just see a point which is only the locally optimal. But for global optimization, it is the opposite. Because the true global solution of the optimization problem is found, and the compromise is efficiency, because we have to find the global optimal solution for these problems. And because it will cost the efficiency, so it is used for problems with a small number of variables, because the computing is very because the computing time is very critical for this problem, and value of finding the true global optimization is very high. And furthermore, convex optimization plays an important role that are not convex, such as the initiations for local optimization, convex heuristic for non-convex optimization, and bounds for global optimization. And here comes to another important question. How we can use the convex optimizations? There are two directions. First is as potential users of convex optimization, and the second is as researchers developing a convex programming algorithm. And realizing the importance of the convex optimizations. So how can we recognize uh, convex optimizations? Recognizing an least squares problem is straightforward. We only need to verify that the objective is a projective function, and the basic least square problems has a simple fixed form. Several standard techniques are used to increase its flexibility in approaches. For example, the weighted least squares. The weighted least square codes, uh, for example, in the objective function w1 to wk, w1 to wk are positive values used to minimize the objective function. Here, the weights wi are chosen to influence the solutions. Another technique is the regularization, in which extra terms are added to the cost function. In the simplest case, a positive multiples of sum of squares of the variable is added to the cost function. You can see in the objective function, the p is larger than 1. And the actual terms penalize the large value of x, and results in a sensible solution in cases. If we want to minimize the first terms, the parameter p is chosen by the users to give the right trade-off. And for recognizing the linear programs, it is not as easy as to recognize least scale problems. In many cases, the original optimization problems does not have a standard linear program forms, but it can be transformed to equivalent linear programs using special techniques. For example, take the chap-by-chap approximation problem as example. It can be solved by using the equivalent linear program and transformations. Most of cases, if we can formulate a problem as a convex optimization, we can solve it efficiently. However, recognizing a convex functions can be difficult. And furthermore, there are many more tricks for transforming convex problems than for training the linear programs. You will find that it, the convex of the many problems can be solved via convex optimization if you learn how to recognize or formulate the convex optimization problems. That's all. Thank you.